In this video, we will go over the various approaches to build effective simulators to train autonomous systems.
This video is part of a 5-part series, and you will find the links to the other videos in the comments section. Autonomous systems use the concept of deep reinforcement learning to train their AI agents. Deep reinforcement learning uses trial and error and the concept of a reward function to tell the neural network whether an action was appropriate or not. Because of this, the agent needs to train on a simulator, as using a real-life system is clearly not an option. There are multiple ways to build a simulator. The first one is to use the laws of physics and the mathematical equations that represent your system to simulate it. A second option is to build a custom piece of software specially adapted for your unique situation. You can also use off-the-shelf software packages that offer numerous simulation options.
In some situations, however, building an AI to simulate a system is the only viable option.
Finally, the last option, when available, is to use a digital twin that your equipment manufacturer may have provided you. Before I go into more details about those 5 simulation strategies, I wanted to quickly mention the concept of adversarial training, where 2 instances of the same software are training each other's. Although this is a very powerful and fast method for training an AI, it's only applicable for applications such as gaming. For instance, this is the model DeepMind from Google used to train its Go AI. A first approach to simulate a system is to use the laws of physics and their underlying mathematical equations to build a simulator. Although it's a very enticing approach for all the engineers among us, it has many limitations. First, it's limited to very simple systems, because as soon as the complexity evolves, even slightly, the math behind it becomes easily unmanageable. Second, it requires specific competencies. If you're a mining company, you don't necessarily have the mechanical, hydraulic, or electrical engineering expertise to build a physics-based simulation of a drill, for instance. And obviously, building those simulations is extremely time-consuming, and any change will require redesigning them. Simply put, physics-based simulation, although theoretically interesting, are very unlikely to be appropriate for autonomous system projects. Another option is to build your own custom software. This is very interesting in particular situations where your setup is so unique that there is no off-the-shelf solution that you can use. However, it can be very expensive to build it and still be very hard to adapt if any change occurs. It will require high software maintenance costs, including ensuring that no knowledge is lost because people have moved around or out of the company. But as you can see in this real-life example on the left from one of our customers, this is a potential option in some well-defined situations. The third and the most popular approach is to use existing software packages, for instance from one of the market leaders such as AnyLogic or MATLAB Simulink. Those are very flexible, very powerful softwares, and they have extensive libraries that can adapt to many approaches from physics-based to flow-based to state-based and so forth. Their libraries and the software are all maintained by the software vendors, which reduces your maintenance costs or risk of having the knowledge leaving your company. However, those being software solutions, they will obviously require recurring OPEX to keep them running and could, over the long term, add up to a significant cost. An evolution on the custom software physics-based and software packages approaches is the concept of digital twins. These have become more and more popular in the last few years. To simplify, digital twins are manufacturers-provided equipment simulators. They will remain connected in real time with the live equipment. This ensures that the simulator state is always in sync with its analog counterpart. The simulator state never drifts from the real-life one. One of the limitations is that the equipment provider needs to provide the equipment's digital twin. It's also limited to the equipment that the supplier offers. If your system is built on multiple machineries connected to each other and coming from different manufacturers, you won't be able to easily connect all of those different simulators in one overarching one. The last major option is to build a custom AI, a black box if you wish. They will simulate your system's all-up inputs and outputs without getting into the nitty-gritty of simulating all of its components. It will simulate the behavior of the system, not the system itself. It can also adapt because it's an AI to virtually any type of system and will fit exactly your situation, and given the right amount of training, it could be fairly resilient to some changes in the equipment or environment, for instance, some wear and tear. However, it requires lots of data and expertise to build. So let's drill down a bit more into this concept of AI-based simulators. An AI-based simulator will need three key components. The first one is a clear definition of all of its inputs and outputs. As mentioned previously, an AI simulator will simulate a system by simulating its behavior, and therefore the state of the system based on a given set of inputs. For autonomous systems, thanks to the machine teaching approach, we'll be leveraging the expertise of operators, process engineers, and R&D engineers to define what are the relevant inputs and outputs that this simulator should support. The second element is going to be the actual AI architecture that's going to be used for the simulator. I've listed here some of the most popular architectures that exist, but there are many more. And they're often linked with the type of simulation one is trying to build, which also includes the type of inputs and outputs. Although new tools have been developed and are developed to more easily build or select an appropriate architecture for a given problem, very often you will need internal or third-party expertise, such as an integration partner, to help you define the most appropriate architecture for your simulator.
The third key element in building your AI simulator is to have enough training data. In the world of deep neural networks, it often means a minimum of hundreds of thousands, or more likely one or several millions of individual data points. Fortunately, as your system is already operational, setting up a logging mechanism to record the process inputs and output states could be sufficient to generate the needed training data. However, in some cases, additional data is going to be needed for this simulator to truly represent the situation in which the system will be. This data, although not being directly connected to the control system or the equipment, can be crucial for an autonomous system to appropriately do its job. Examples of such variables abound. It could be the sound that the machine is making, the output visual aspect, the reaction of a machine to unusual user inputs, the stocks of products in the supply chain that are stored not where they're supposed to be, the external conditions such as weather or humidity, and so on. To capture this additional data, further development will likely be required.
For instance, in one of the projects our team worked on, we used a custom vision model to capture the visual characteristics of a snack. Then the data from the custom vision model was combined with the regular process data that the controller was providing, and these were used to create the data set needed to train the simulator. If you want to learn more about how the team developed that, please refer to the video about the real-life example that is linked in the comment section of this video. You should carefully look at three key aspects of autonomous systems simulators. First, always remember a simulator is never perfect. It is critical to know beforehand the simulation's limits in terms of precision or any other aspect. Second, as the equipment evolves and, for instance, faces a regular wear and tear, it might be very important to revalidate or even fully retrain your simulator. This potential drift will be less of an issue if you use a digital twin because the digital twin synchronizes with its real-life counterpart. Finally, and this could be the trickiest part, you need to ensure that the simulator input range will mimic the real system input range. You need to ensure that the range for which your simulator functions is the same or is larger than the range that you will see in real life. For instance, if your simulator was trained with data assuming temperatures from 200 to 400 degrees, but the real-life system could go as low as 150 degrees or as high as 500 degrees, it could be very problematic when the system reaches those extreme values. In this situation, your agent wouldn't have been trained for these ranges of inputs, and its action will be quite unpredictable. Let me double-click on this concept a little bit.
One way to think about the application scope is to think about an operational universe. Operational universe refers to the range input variables could have in a real-life situation. In this simple two variables example, you could define the minimum and maximum temperature and pressure for which the system should work. Obviously, the vast majority of systems that you would want to control won't have only two variables to take care of. In this other example, we added speed of the machine as a third variable, and you can conceptually represent it as a three-dimensional operational universe. In most situations, the number of important variables will be much larger than 3, and obviously it's not possible to illustrate that graphically, but I hope you understand the overall concept. In addition to the number of variables, this example was also very simple in the sense that any pressure and any temperature within the acceptable range are working. However, in most situations, you won't be as nice and linear as this picture looks like. There could also be different ranges with different form factors.
In this still simplified view, you can see how different ranges of temperature correlate with different ranges of pressure and speed. Therefore, when you build your simulator, you will have to ensure that either it can adapt to those different scopes, or you might need to create 4 different simulators for those 4 different sets of parameters. This concludes our video on simulations for autonomous systems. Please check the comments section for direct links to the other videos of this series, and feel free to leave comments or questions and we'll do our best to reply.